Hello, everyone. Welcome to SIGGRAPH 2025 OpenUSD Day. Hopefully, you're very excited for today. We have an exciting lineup of sessions for you, diving deep into the future of OpenUSD. To kick things off, we're joined by Vice President of Research at NVIDIA, Mingyu Liu, for Beyond Rendering, Why Graphics Are Needed for Physical AI. So please join me in welcoming Mingyu Liu to the stage.
Cool. Okay, so I'm very excited to be here. We're gonna talk about OpenUSD and how OpenUSD can help with physical AI. My part of presentation will be from a different perspective, how Gen AI can superpower OpenUSD to enable physical AI. Of course, Gen AI itself is also a key component to enable physical AI. So Gen AI, all of you are familiar with now. It can be used for content creation, chatbots, digital marketing. It's very successful. We are able to build powerful Gen AI model because of huge amounts of internet scale data. Agentic AI is Gen AI with tool use. With a compiler, editing tool, use Gen AI to control those tools to achieve something more amazing. And agentic AI gonna be also very successful because we have a lot of training data. People are using tools, those are recorded, and then we can train AI to achieve better capability. To make physical AI successful, physical AI is, you can consider not just tool use, it's a physical tool use, something that really moves. They can perturb the state of the world, right? To make it successful, you also need a huge amount of training data. And graph is the key to create the training data, especially because we don't have those robots surrounding us collect data at the first place. We need some creative way to create initial training data to set the scene in motion. And graph is the key. Graph is superpower with Gen AI is the key. So large scale data, large scale digital tool use data, and large scale physical AI data. And this is the physical AI data pyramid that we believe the right recipe toward the success of physical AI. You start with huge amount of internet scale data, those videos capturing different interaction, assembling an IKEA chair to cook a nice meal. You use those internet scale data to build a world model or some kind of understanding of 3D world, and use that powerful world model to start to generate synthetic data with the help of graphics pipeline, those exceeding physics simulation engines and 3D representation in the USD formats. Together with in-robot data. In-robot data is important because in-robot data is the data that contains the observation and action pair to make the connection from the visual world that we are familiar with to the action space that robot need to take the right approach, the right action to complete the task. So as a media, we are building this world model called Cosmos. It's actually a world foundation model platform. We want it to be a backbone component that all of you can take and build your own world model and to turbocharge your physical AI applications. Use Cosmos to create synthetic data. Now it's not just internet scale data, it's a synthetic data from the robot perspective. It can be multi-views. And also, we can leverage Gen AI to create feedback that what we human might experience in the real world. Together with in-robot data, then we can train a physical AI agent to be successful. I'm gonna play this movie. I think this might be the movie bring many of you to computer graphics.
How was he? 10 hours straight. He's a machine. I know Kung Fu. Show me.
I think many of you are attracted to computer graphics because of special effects, demonstrated in the video. But another important concept bring in from this movie is the world model. a huge simulator that can simulate the activity that might happen in real world. From those simulations, you gain experience and gain skills. And what we want to achieve here is not to train you, we want to train robots to become capable to handle real tasks for us. So we want to build a matrix for robots, and the good one, not trying to eliminate human beings, right? And to me, the world model is the matrix. I know that in robotics, there's a formal definition of world model. Here I'm taking a more general definition. It's the matrix, right? So basically, we think Cosmos is the matrix where you put an agent, the environment, maybe the dojo, the task, Kung Fu. You enter and you come out with an agent capable of doing the task. Let's go to the specific example here. I'm gonna use a couple of things interchangeably. One is the world model. The other is the generative training facility. This is a training facility to train robot agents. In generative, it leverage huge amounts of generative AI. So here, the agent is a robot policy. A policy model is a model that's based on the visual observation. It's control robot to take certain action. And the environment is a kitchen, and the task is pick up a knife and cut cucumber into slices. Initially, the robot policy doesn't know how to do it. But through this generative training facility or matrix, we want it to come out with an updated robot policy with a skill to achieve the task. Now, when we start to augment the environment, not just one kitchen, multiple kitchens, then we expect the updated policy can handle the task in many different environments, many different kitchens. Because handling can handle many different kitchens, there's a possibility to generalize to unseen kitchens. Similarly, you can augment in the task space. Instead of a single task, you have many tasks. And you can begin insertion, cuts, and then the robot can learn new combination that you didn't teach it during training. And you can augment both environment and task. Then you have a powerful agent that can handle many, can have many new skills for many new environments. For driving, autonomous driving, similar, right? Now you have a driving policy, and the environment is a roundabout. The task is cut into the roundabout and take the third exit. And through this generative training facility, we want to come out with an agent that's capable of handling this. So you can think you can build your self-driving car this way, one skill by one skill, and eventually you can handle unseen skill and then navigate in the real world traffics, or in simulation, training simulation. All right, so to build this generative training facility or the world model, we believe there are two fundamental capabilities that we need to build. One is world understanding, understand what happens, spatially and temporally. The other is generation, the capability of simulate what's gonna happen in the future, or think about alternative appearance. So this is the algorithm. So basically, here state is the representation of the world. The policy, the controller of robot, look at what it sees, and based on the instruction it was given, try to take the action to complete the task, pick up the knife, right? Once the robot take an action, it perturbs the world. This is not a digital tool, it's a physical tool. It perturbs the world. And based on the action, the world generation part of the matrix react to the action and update the observation, and then go to the policy. So keep doing this until the robot is done. Once the robot is done, you have final state as capital T. And based on the understanding, we know whether the knife is really picked up, or whether pizza is really put in the oven. And based on the result, you have a reward R. And reward used to update the policy. And here I'm talking a more general, world model. I know that so far in Cosmos we mostly model visual world, right? But you can think a tactile sensor can also convert the touch into a video in a different domain. Yeah, so this can also be modeled in that space. All right, and building the metrics gonna take a long time. Hopefully not too long, but with the acceleration of technology and a lot of excitements like every week, I think it might come very soon. But before we reach the final goal, the metric, in the intermediate component that we build are useful, right? For example, we can use it to generate synthetic data in passive way, right? Generate different, driving with the different weather conditions. This environment can be used for passive evaluation. Those intermediate output can be useful. We don't need to wait to the end. Okay, so here I'm gonna give a more formal kind of introduction to the Cosmos World Foundation model. So in this platform, Cosmos World Foundation model platform, our goal is to enable our developers to build the matrix for their own physical AI setup. For that purpose, we build pre-trained the foundation model, pre-train the world generation model that you can fine-tune, you can post-train toward your own physical AI setup. We build pre-train the world understanding model that you can post-train for your own physical AI setup. So not just releasing the pre-trained foundation model, we also release post-training scripts to help you adapt. Give you one example, right? So different self-driving cars have different number of camera at different positions, looking at different directions, right? So to build a proper world model for your self-driving car, we need to be able to generate multi-views. And only the physical AI developer, for their own specific setup, they have the training data to do it. But it's difficult for them to collect enough data to begin with to build a world model. We do the heavy lifting first, getting huge amounts of training data, build a good base, and then can be post-trained to become multi-view. And to enable people to do that, we provide post-training scripts optimized so that you can build the model faster. And curation, data curation is also an important part of building this foundation model. We also provide curation tool to help you. Video curation requires a lot of video processing, and the GPU can be very helpful to accelerate the processing, and we have spent decades in making those tools. Now we bring them in the curation pipeline to enable you guys to process video, to curate data faster. All right, so this figure shows that our goal. We build pre-trained the world foundation model, and customer maybe driving, self-driving car, industrial robotic arm, robotic dog, humanoid robot. They can use their custom data set to post-train the pre-trained foundation model and to have a world foundation model for their downstream applications. And we open source everything. We have that I'm going to talk about. We have 3 main model, reason model, world understanding model, Cosmos transfer, and predict. Both are world generation model. We also have a Cosmos curate. It's a curation tool that I mentioned earlier. We also have IO, which is IO library to help you post-training. All of them are available in GitHub. And all our pre-trained models are available in Hugging Face. Okay, so let's go deeper into Cosmos World Foundation models. So we have 2 sets of models. For world generation, we have predict and transfer, and the understanding model, world understanding model, we have Cosmos reason. So Cosmos predict, take the past few observation, the current frame maybe, and test prompt, and generate the future frames. We build the Cosmos predicts based on diffusion model So it's a model that's there's a forward and reverse process. In the forward process, you take a video and you gradually add noise to make it purely render noise. And we learn the reverse denoiser to gradually remove noise, eventually give you a clean video. And we use a diffusion transformer architecture. So the detail is in the paper, but just now most of the video model are more or less the same. So it's very standard diffusion transformer, but the key is how you train the model. So once you have this Cosmos predicts, right, initially just take test prompts. You can start to add camera trajectory as an input post-train, through post-train. You need a subset of video where you have detailed camera pose annotation. You take this camera annotation and the video as a pair to post-train the Cosmos predict. Then you can achieve something like what you have seen in Google Genie 3, where you can go forward, backward, left, and right. You can navigate in a world that you create. And here's another example: shopping in the supermarket and going to different direction. Here is another example in the industrial setting. Not just you can train it to output one view, you can train to output multi-view if you have multi-view training data to begin with. You have, let's say you collect multi-view data and you have them synchronized. Then you can start to use them to post-train the Cosmos predict model to generate different view like what you need in a self-driving car. And in addition to predict 6 views, you can also make it condition on the vehicle trajectory, how you're gonna steer the car toward different direction. Here the radar shows the vehicle trajectory, and this corresponding multi-view. You can pretty much drive a car in this virtual world. And you can change the test prompt to instruction. Hey, say that organize books by placing them vertically on a shelf. Based on instruction to generate the future outcome. And it can also be post-trained to condition on the robot signal, like how the motors, the signal you send to the motor to control the motion of the car, the any factor. So I hope till here you see why we want to create this base model to help people to continue to post-train for their setup, because different robots really have different way of control different walls. So it's very difficult to have one model that serve every other models, every physical AI devices. So I also want to talk about Cosmos transfer, and this is particularly useful for in this OpenUSD context. So it's a model that do the photorealistic world states augmentation. So the world states can be represented at different modality, and through the Cosmos transfer, you can come out with different simulation. So we use a multi-control net block to implement this one. So we remember in the Cosmos predict, we have this diffusion model, and we build several control branches, and each branch take different modality input. It can be edge, can be depth, can be segmentation, and they can be combined together. Here I'm gonna show a video. So different control input modality and can be used as condition to Cosmos transfer to generate photorealistic outputs. So here you see the HD map, one input, but you can generate multiple possibility. to create the appearance variations needed to train your self-driving agent to be robust to appearance change. Another example based on LiDAR as the input. Okay, so now I want to talk about Cosmos Reason. It's a world understanding model. You can consider it's a multimodal LLM specialized for physical AI. What do I mean by specialization is it's specialized for spatial understanding, temporal understanding, and physics understanding. So in our model, it takes video and text prompt as input and generates a channel of soul reasoning trace and come up with the answer. And the architecture is like this. You have input video and use a visual encoder to convert the input video into tokens. And those tokens are mapped into video tokens together with text token into the LLM. And the LLM come out with a syncing channel of soul reasoning trace and then come out with the answer. So what we do differently is we create these two stages. One is physical AI SFT, supervised fine-tuning, and physical AI RL. So we want the Cosmos Reason model to possess great capability for physical AI, and we believe these are two important things. One is a physical common sense reasoning, the other is embodied reasoning. For physical common sense reasoning, we believe there are three important divisions: space-time, fundamental physics. And based on this, we create subcategory, right? For the space, we have understanding of relationship, possibility, affordance. Time, we have action, order, causality. And fundamental physics, we have state, attributes, object permanence, and the anti-physics, like people cannot fly. And we curate training data to train the Cosmos Reason model to be good at these aspects. And embodied reasoning has something to do with the shape, the physical construct of the physical AI device. And we believe there are four important parts we need to cover. One is process complex sensory inputs, predict action effects, respect physical constraints, and non-found interactions. We have a detail written in the paper, so I welcome you to check it out for more details. These are the detail breakdown, and we pretty much use these to go to create training data set to go through this physical SFT and physical RL. And one of the ILO tasks we train the model, pretty interesting, is we enter a video to the model and ask the model to say whether this video is play forward or backward. Let me quickly ask the audience here. Is the first video play forward or backward? Yes. How about this one? Yeah. How about this one? Backward, right? So these are video you can easily get a verifiable reward. You know whether the video is play forward or backward. And you challenge the Cosmos Reason model or your own VLN. And it forces to understand the causality, right? For example, when you're putting water down, the water should go down, right? When you see a video, water comes up, then it's anti-physics, right? So that's how we train this physical AI reasoning model to be capable to help us under the spatial context. All right, and when we specialize the model in our target test, we are able to achieve better performance compared to model like Gemini and GPT. So I'm gonna skip this part, and basically what I want to say is our goal with Cosmos is to enable everybody to build the matrix for their physical AI setup. And I think it's time to take questions.
So I think it's a very good talk, thanks. I'm a graphic compiler engineer. I also like movies. You use the matrix. I have a question. So what kind of a quality you want your like graphic quality you want the training data to be? Because on one side, you in the matrix, you want is as real as possible. On the other side, you also mentioned the like some kind of a modifier. It's kind of an inception. Another movie is tricking the robot to think is in a special condition. So you can train it, the robot, say, colorblind, and they still do the thing. So that's the question. I'm not sure I make it clear enough.
Yeah. So I think it's a good question. Thanks for your question. I think the main question is on the fidelity required, right? So appearance fidelity is important. Physics fidelity is even more important. Yeah. So I would say, so what I see is people are adopting vision language action model as the controller now. So vision language action model take a VLN and change the output to instead of text become action. And those vision encoder actually can handle certain amounts of visual variations or imperfection in the rendering. Right, so I do feel if you let me choose fidelity and physics correctness, I will choose physics correctness whenever we have a trade-off need to be made.
Great, thanks. Okay. Thank you.
Okay, so maybe this, yeah.
In your experience, how do you balance the pre-training versus post-training? In terms of how much they impact how well the model does at runtime for, say, reasoning, predicting, style transfer, etc.
Thank you for the good question. So, our goal is to build a very powerful pre-trained model to make post-training easy, right? The more powerful the pre-trained model is, the easier the post-trained task could be, right? But there's certainly mean we can achieve because different physical AI have different setup, right? So from my side, I'll go to make pre-trained model as good as possible. And so we want to bring many things that in post-train can be done to pre-train. Yeah, that's our goal, yeah.
So do you want to own the post-training as NVIDIA? Or
No.
do you want to leave it to your users?
We want to leave to customers so that they can post-train, but we also want to reduce their burden, right? So with a more powerful pre-trained model, tests will be easier, hopefully. Yeah, because there are a lot of different challenges you need to face when you want to build a robot. Yeah, so we want to share the burden.
Awesome. Thank you for the questions. We do need to move on to our next session, but if you have any questions, feel free to come to the developer meetup at 5:30 today,
Okay.
And we can continue that conversation. So please, thank you, Mingyu.
Thank you.